Okay. Can people hear me? Yeah. Okay, so we're going to switch now from graphene-based TMDs to, Moiré materials to transition metal dichalcogenide-based Moiré materials. One of the, one of the most interesting things about the TMD case, as we'll discuss, is that they have quantum Hall states, quantum anomalous Hall states, and it turns out you also have quantum anomalous Hall states in graphene-based systems when they're aligned, when you get a Moiré from aligning with HBN. But the TMDs have the virtue of being much simpler. So that's the case I'm going to discuss. So I'm going to start by making just a simple remark about quantum Hall effect. And I'll come back to this in probably lecture tomorrow. Here I've noticed, if I have a single particle Hamiltonian in some system, then I can, calculate the derivative of this Hamiltonian with respect to a parameter, the magnetic field, and what I get is, if I take, just using the chain rule, differentiating with respect to A first, and then with respect to C, then yeah. Okay, so this is basically velocity, E over C times velocity cross position operator. Okay, so that's just a Hamiltonian identity, and the derivative of the Hamiltonian with respect to B is the operator for orbital magnetization in this Hamiltonian that doesn't have any spin degree of freedom. Yeah. So, we're going to talk about, quantum anomalous Hall states. Quantum anomalous Hall states are basically two-dimensional insulators. So I want you to imagine some 2D electron system of some arbitrary shape with an edge somewhere so that this position operator is bounded. And and I want you to consider the case where, let me just say, what we're interested in is a many electron system. So that means I sum this term over all the particles, and there's also an interaction term, but that interaction term doesn't depend on B. So in the many electron case, what I get is, the orbital magnetization, which is, let's say, at 0 temperature, the ground state expectation value of this orbital magnetization operator is by Hellman-Feynman theorem just integral over space of this, measured at some position. Okay. And the thing I want you to consider is how this expectation value depends on the chemical potential when I have an insulator. And, so from the many electron point of view, what an insulator is a system where the chemical potential as a function of density has a jump somewhere. So that means that chemical potential is, ground state energy to add an electron. This means the energy to add one electron is different from the energy to take one electron away. And so there's a gap for charged excitation. So that's what makes it an insulator. And I'm interested in changing in this finite system the chemical potential inside this gap. So if I do that, then the only place that this local quantity that I'm integrating over position, the only place it can change if I'm changing the chemical potential and I have an insulator is at the edge of the system, okay? And so I'm going to do, calculate this difference in orbital magnetization between two nearby chemical potentials by integrating over space, okay? And so the velocity, expectation value of the velocity operator can only change, at the system. I don't know, here I've drawn an edge, the edge of a system fuzzy. It has some natural length scale. Sometimes it can be quite big, but it's smaller than the entire system size. And so when I do this integral, let's say I choose some coordinates. Well, when I do this integral over position, what I want to do is first integrate perpendicular to the edge in some region, and basically replace the position when I do that at this point on the edge by, some position in the middle of this region, which represents, the position of the edge at that point, which may be fuzzy, but it's not fuzzy on the length scale of the system size, okay? So when you integrate, charge times velocity across the edge, that's the current, right? And so I want to integrate first across the edge and then around the edge. And when I integrate across the edge, it may be that there is a net current flowing at that point along the edge. And we'll see in just a moment, and most of you know, there is, when you get a quantum anomalous Hall effect, there is an edge current. But for the moment, let's just imagine there might be an edge current. And what this orbital magnetization then is the edge current, okay? And by continuity equation, if there's an edge current flowing here, it has to be the same everywhere along the edge. So this edge current doesn't depend on position along the edge. And so this is that I've absorbed E times V into a current density. And I've forgot a factor of 2 here. And then I have 1/2 integral dr. And now I integrate along the edge. So this is an R on the edge. And I'm going to integrate around the edge. And, CGS units. So just to help me find if I made a mistake. And so this, of course, 1/2 the integral of R cross position on the edge is just the area of the system. So this should have been integrating, integrating along the edge. R is a position on the edge. I'm not sure, maybe I should call it L. Is that what you want? L is a position on the edge. You're dotted with BR cross R. This I shouldn't have done that. This was I shouldn't have written that. It's not a dot product. This is D2R, and this is this cross product of these 2D vectors. That's a scalar, yeah. Okay. Yeah.
B, get the I, B was heading along the edge. You're taking B to be along the edge, right?
I'm taking DL along the edge.
DL.
Yeah, so separate the integral into an integral perpendicular to the edge. Okay, that gives you the edge current at that position on the edge. But the edge current has to be the same everywhere along the edge. And then I'm integrating, let's say,
Once you integrate over cross section, just a constant now.
yeah. And so this is just little elements of the area, right? So this integral is just a way of writing them. So we have I edge times entire area of the system, and CGS divided by speed of light. So I've assumed nothing here, other than I have a 2D insulator, and I allowed there to be edge current. Go ahead. I'll say that again. It's the orbital magnetization, yeah. Yeah, so this is the orbital magnetization. And now, because I want to insist the current density, well, I want to calculate the derivative of the orbital magnetization with respect to chemical potential, changing the chemical potential somewhere inside this gap where nothing is changing in the bulk. And that's what allowed me to say that, the derivative of this the current, if you like, with respect to chemical potential is only non-zero on the edge. It's because we're in the gap. Make sense? Yeah, go ahead, you can help me. Yeah, so maybe my notation is awful here, but so what I'm doing is I integrate across the edge, okay? So now at every point on the edge, I've done the integral across the edge. Now along the edge, right? And so let me call L a position on the edge, and I'm going to integrate around this curve. And L cross DL for a singly connected curve like this is twice the area. Yeah, so I call this, let's say, L. It's a position base that's on the edge. And then I'm going to take it around the edge. Okay. So DL is along the edge, along the local direction of the edge. And I integrate the current perpendicular to the edge. Go ahead. It's just because if I think about doing this integral, this is just, I have little triangles, right? So, is it a version of Stokes' theorem? Yeah. Let me see. What about the 1/2? So where did the 1/2 come from? It came from here. Okay. And this local, this local little element here as I go around the edge of area. Yeah. So where did the 2 come from? It came from the gauge I chose, and you get the same result with any choice. Yeah.
Why it's confusing is to me is more not the integration.
Yeah.
The derivative with the chemical potential. Can
Yeah.
you elaborate? Like naively, I look at the topics equation 2 from the bottom. That equation.
Yeah.
Where's the chemical potential there?
So this is the expectation value in, the many body ground state, which will depend on chemical potential of this sort of local current density, if you like. V of R, it's
It somehow then took that integral and it takes the 2D integral, well.
so this, let's say V of R, or if I multiply it by E, J of R is an observable, a local observable, say. And doing sort of like many body physics at zero temperature, so chemical potential is a parameter. And so I'm differentiating with respect to that parameter, which I haven't explicitly indicated here. But the key thing as I'm making the argument is this is only trying to make a statement about what happens when the chemical potential's in the gap.
I see everywhere else it's zero, derivative is zero.
Yeah, yeah. So the current density changes when you change the chemical potential are at the edge. Yeah. Anything else? Yeah. Say that again. The position at the edge. So let's say this is just a curve. So all I've written here, this is the vector that goes from some arbitrary origin on the edge. No. So I'm just saying that there might be a current density at the edge. If there's a current density at the edge, it can change if I change the chemical potential, because something at the edge, even if I have a gap in the bulk. So the origin, so here I've said it's, the change in this, it's really dV of R d mu, right? But I'm saying that the only place that's non-zero is at the edge. So I can integrate across the edge to get the total edge current, which by the continuity equation can't change as I go around the edge. And what's left is just the area. So this is a very general result that doesn't depend on anything, any detail, right? That dm orbital d mu is, and this I edge is really.
Okay, now it's good.
Okay, yeah.
Yes. A times I is the magnetization.
Okay. Yeah. Okay. So that's just a statement about two-dimensional insulators. And, what I want to claim is when people measure the quantum Hall effect, a fully developed quantum Hall effect, which has, as you know, quantum Hall effect is an example of dissipationless transport, right? And what they're really measuring is just this thermodynamic quantity. It's not really a transport quantity. It's a thermodynamic quantity, di edge d mu. And so maybe I'll do it here. So here I finite area 2D electron system, and let me connect it to leads, okay? And let me just do so here's a current source and a drain, okay? And so what happens when you have a quantum Hall effect is, as you'll see in a moment, you must have edge dates. Along each of these edges, they're sitting in this gap, right? They're very far away from the other edge. So inevitably, this won't happen immediately right at the contact. But as you move away from the edge, you'll have a local equilibrium along the edge at some chemical potential. Here I've called mu bottom. And similarly, on the other edge, you'll have a chemical potential mu top. And so if mu top is different from mu bottom, that means the edge current in this local equilibrium region will be different from the edge current in this local equilibrium region. And the net current that flows through the external circuit is just the derivative of the edge current with respect to chemical potential times the difference of these two chemical potentials, okay? So the quantized Hall, what's called a Hall resistance in or Hall conductance is really just a measurement of this thermodynamic quantity. And and we can say one more thing related to this. So di edge d mu. The thing that I'm claiming is, actually measure when you do a quantum Hall effect experiment, just a thermodynamic quantity, is derivative of the orbital magnetization with respect to mu. But the orbital magnetization, as we said at the beginning, in terms of ground state expectation values, is the derivative of the ground state expectation value with respect to the minus sign here. D mu, minus sign here, dB. And this is, some kind of Maxwell's relation. dE d mu at zero temperature is minus the number of particles. So this is dN dB. So when you measure a quantum Hall effect in the presence of a magnetic field or in the absence of a magnetic field, what's called the anomalous quantum Hall effect, really what you're measuring is that there is an edge current in equilibrium, and you're measuring the derivative of that edge current with respect to chemical potential, and that derivative has to equal the magnetic field dependence of the number of states, the density here, if you like, the density at which the chemical potential jumps, let me call it n star. When you have a quantum Hall effect, that means dN star dB is not equal to 0. Okay? And so, we know, and this is, of course, the historical example of the quantum Hall effect, the one in a 2D electron system in a magnetic field. We know an example where you have jumps in chemical potential and, the density, a number of states, or the density of states at which the chemical potential jumps occur depends on magnetic field, and that's the example of Landau levels. Each Landau level, as we has a density that is proportional to magnetic field. So let me calculate this thing, and I forgot to put these other factors here. C over A. So we know dN dB for a Landau level. I'm not going to do the quantum mechanics here, but I think you all remember that the number of states that fit in a Landau level is the number of flux quanta that go through a 2D system. So if I fill, for example, one Landau level, N is equal to BA over flux quantum phi naught. So that's And so the NDB is just A over phi naught times C over A. And if I remember that phi naught is HC over E, this becomes, or E over H. And that's what's measured when you measure the quantum Hall effect. Of course, you know, people, when you do measurements, you characterize the difference in chemical potential between the two edges as a voltage. So there's an extra factor of E. So dI, d voltage is E squared over H, okay? So the quantized quantum unit of resistance. Okay. So I want to insist that these things, you know, that when you measure quantum Hall effect, really measuring that you have a local equilibrium on the edge. And you're measuring, and then if you, then you're measuring this thermodynamic quantity, which is also this thermodynamic quantity. Okay, go ahead.
If the current was not localized on the edge, I think there's still, the result would not change. Like if you had impurities and it was kind of.
It would be more complicated, right? I mean, well, I think it would be more complicated because, you know, this argument depended on the fact that the current density is only changing at the edge of the system. If it's
this Halpin's calculation, the Landau flow,
yeah,
floating up at the edges, you know, it doesn't change. It was a boundary term in a sense, like if you create some wiggles at Landau level from local chemical potential variation, it would.
Well, yeah, chemical potential is really not defined in the bulk, right? Because there are no states there. So you're thinking of,
that's
you know,
impurities.
Yeah, you can make not a chemical potential variation, but electric potential variation, if you like, and that's fine. So this allows any kind of disorder potential, any kind of electron-electron interaction that doesn't depend on anything.
Kind of the potential.
Yeah, so this, right from the beginning, I have a random potential here. But I am assuming when I write this that there's an actual charge gap. Many times when people measure the quantum Hall effect, it's only a mobility gap, right?
Oh, I see, right, that's the difference.
And so there's an extra, you know, few words you have to say. I do have states at the chemical potential, but they're localized, so they don't matter.
So
but
that would just add some local currents going around loop.
Yeah.
Rather than going all the way around. And so they would not affect.
And they wouldn't be affected by chemical potential at the edge.
I see.
Right. Yeah, go ahead.
Non-quantum Hall system, I'm measuring electrical resistivity. You know, I apply a gradient chemical potential, I measure the current, I change the chemical potential gradient of it, I see how much the current changes. Would you call that a thermodynamic method?
No.
So what's the difference?
There's dissipation, first of all.
Okay. So I guess my question, why do you call this a thermodynamic quantity?
Because it's just derivative of, you know, it's
because of the left-hand side.
Yeah. It's just the orbital magnetization and how it depends on chemical potential. That's thermodynamic. It's not okay?
Okay.
Yeah. So we'll come back to that. Okay, next thing. Okay. Yeah. Okay, so we're going to talk about transition metal dichalcogenides. These group 6 semiconductors. There are 5 of them that form the structure. I'll say a little bit more about in just a minute, and they're all semiconductors, right? So there are, even if you take these 5 systems, you know, there are 15 possible even bilayer combinations. So there's an awful lot to explore. Even for bilayers, most systems have not been studied yet. We're going to concentrate on the ones in red here, which are making a bilayer where the two layers are the same material, a homo bilayer, and it has if you have a homo bilayer, you can have a Moiré pattern just by twisting. Okay? In these materials, it turns out that it turns out that the lattice constant, just chemically, is determined almost entirely by the chalcogen atom. So the ones in yellow here are not homo bilayers, but to get a Moiré pattern, you need to twist them nevertheless, because the lattice constants are almost exactly the same. So on the right-hand side, I've shown you an electronic structure calculation band structure calculation that we did a decade or more ago because of some experiments by my colleague Emmanuel Tutuk on tungsten diselenide trilayers. Okay, and so I'm not going to talk about trilayers, but there's lots of things to play with when you go beyond bilayers in these systems. And all I'm trying to show you here is that, what turns out, and I'll come back to this in a moment, that in the equilibrium structure, at the top of the valence band, and we're going to be interested here, in this case, this momentum K, the same momentum in the corner of the Brouin zone that we were talking about in the graphene systems. And it turns out that they're practically not coupled from layer to layer, okay? And there are states not too far away at the center of the Brouin zone, and they are strongly coupled from layer to layer. And so what happens is, as you start to add more layers and the wave functions can spread out, the energies basically don't change at the Brouin zone corner, but they do change a lot at the gamma point. They basically spread out. And so in bulk material, the top of the valence band is at the gamma point in the Brouin zone. This was something understood very early on in connection with the important optical properties of these layered systems by Tony Hines and collaborators at Columbia, a Kin Phi Mox PhD thesis maybe, that when you go to single layer, the top of the valence band is here. And this is actually an experiment in a tri-layer where you can fool around with gates and you can move charges back and forth between different regions of momentum space. But I've had many versions of this figure over the years. And, so this says in a bilayer is, this notation, the red ones are the homo bilayers. And this notation says, is the top of the valence band at the Brouin zone corner or the Brouin zone center microscopically? And, it turns out DFT doesn't get this right, more or less. You have to trust experiment. And so I think we now know that there are 2 of these 5 materials. And these are the materials I'm going to be talking about with very special but simple properties where the top of the valence band is at the K point. Okay, so that's what we're going to be talking about. Okay. Oh yeah, I should have said one more thing. Sorry. This calculation is just one that I could grab conveniently, so it happens to be for a tri-layer. And so there are, and it's at a non-zero displacement field, this calculation. The dashed lines are anyway. And so you can see that, all of these states are more or less localized in the layer, right? And so if you apply a transverse electric field, then in this tri-layer, there are 3 different states at the top of the valence band. That's not what we're going to focus on. But the first thing I want to say is that this system does not have inversion symmetry. So Kramer's theorem doesn't guarantee spin degeneracy of Kramer's degeneracy of bands. There's only one state here in each layer. There's a very large spin orbit coupling, which is, as you see in that picture, around half a volt at each momentum. And basically, we're going to ignore, because we're interested in energy scales smaller than half a volt, the spin orbit couple state. And so if I, yeah. So that's the only thing we have to know. There's only one state in each layer at the top of the valence band in the energy range we're interested in. So what I'm going to say now are just some words around calculations you can really do, but just explaining qualitatively. And this is, this is a notion, if you like, for building a continuum model of these systems. The notion that's based on imagining that I have a tight binding Hamiltonian as a function of stacking. And I get, that in the Hamiltonian, the stacking is some slow function of position with varies by a lattice constant when you go by a Moiré lattice constant in position. So I'm going to try and say a few words about how the Hamiltonian of this system depends on stacking, okay? And because, yep.
Before you go on, my understanding TMDs have the quadratic dispersion rather than the block point.
Yeah, that's correct. That would be important. Yeah. So this is the quadratic dispersion. If you look at one of these black lines, for example, this is an, so this is for a crystal with actually the thermodynamic equilibrium stacking. So it's not a Moiré system, and you have quadratic dispersion.
Is that just because A and B is broken, the inversion symmetry is broken by the 2 different atoms? You basically take Dirac and you get a mass, add mass to it? Yeah,
no, maybe it's more that, in graphene, there are 2 pi bands, and at neutrality, you fill one of them. And in graphene, it happens that at the Brouin zone corner, the hybridization between the, for the equilibrium structure, the hybridization between the 2 different pi orbitals vanishes between A site and B site. So you just have localized orbitals on A site and B site. So that's what gives you the Dirac point in single layer graphene. So now in the individual layer, we just have, at a given momentum, there's just one state. Okay, there's no others, there's no sublattice. I'll come back to say some more.
There's the AB sublattice. Oh, sorry, there's 2 atoms per unit.
Well, actually, there are 3, right? So 1 metal and 2 chalcogens, but they're different. They're not both carbon orbitals, and they have different energies. Okay. And so that's an important thing you're reminding me to say. These are mostly metal, these orbitals that are at the top of the valence band. Okay. Yeah. So the model Hamiltonian, or the Hamiltonian that describes this system at the reference wave vector at the center of the Brouin zone is just a 2x2 matrix, okay? And so that means, unlike the case of graphene where, so let's say what we had with graphene, for each stacking, we actually had a 4x4 model, right? Because we had the 2 pi bands, coupled pi bands of single layer graphene expanding around the Brouin zone corner. Momentum gives this Dirac dispersion in each layer. And then we had to have a 2x2 interlayer tunneling matrix because there are two sublattices. So this is simpler. So this is TMD homo bilayer. Whoops. There's only one orbital in each layer. So this is, again, a layer representation. Turns out that this orbital is, well, the reason the spin-orbit coupling is so big is that this is, this is orbital has the orbital angular, d orbital angular momentum aligned, aligned along the perpendicular to the plane, the z direction. So the spin-orbit coupling is just 2, because it's angular momentum 2, times sz. So that's why normally spin-orbit coupling produces shifts in energies that are second order in the spin-orbit coupling strength. Here it produces a shift that's first order in the spin-orbit coupling strength. And that's what gives us one layer with a particular spin at k. There's also the time reversal partner momentum minus k, and that has the opposite spin and opposite orbital angular momentum. It's a time reversal, partner. Kramer's partner is at minus k. And so now we want a 2x2 Hamiltonian that depends on stacking. And let's say this is top layer. And then we have some tunneling function, which in this approximation is going to be a local function. And it's based on the Brouin zone momentum. It's based on, it's the tunneling at the Brouin zone corner momentum, just like in graphene. Okay, now, where to go? Yeah. So this is actually such a plot. This from a paper from my former student, Fengcheng Wu, who's now at Wuhan University, from a number of years ago. And the color plot is a plot of, plot basically of this 2x2 Hamiltonian, how it depends on stacking. And the color tells you the difference between the potential in the top layer and the bottom layer. And the little arrows, which in this 2x2 matrix with a layer pseudospin representation, the little arrows are the off-diagonal layer terms, tunneling between layers, and the black arrows are showing that complex number as a local magnitude and phase. Okay. First, let me talk about the tunneling term, which is represented on this plot by the length and direction of the black arrows. Okay. And so we can talk about that quickly because we already did it. And to say we already did it, let me remind you that, so this is sort of transition metal dichalcogenide. Each unit cell has 2 chalcogen atoms, 2 sulfur atoms, say, and 1 metal atom. And the structure, if I look at single layer, the structure looked at from above has a triangular lattice of metal atoms and a triangular lattice of chalcogen atoms, of 2 chalcogen atoms in above and below the metal. They also form a triangular lattice, and the chalcogens are, the whole thing together looked at from the top is a honeycomb lattice, just like graphene, but the But with the difference that you don't have the same atoms on each sublattice of the honeycomb, okay? And yeah. So okay. So first let me, Jay, say for the tunneling. It's the same result we got before, okay? Because nothing changes. Except now it's always from metal to metal. If you may remember the expression for the sublattice dependent tunneling in the graphene had some extra phase factor. One sublattice to a different sublattice. Here it's always near the Fermi level, it's always metal to metal. So same sublattice, same logic gives you the same expression. There's a coefficient in front of this that I'm going to talk, that I call W in the graphene case. And I'm going to make a remark about that. So the Moiré patterns in these homo bilayers always come from tilts. And we can consider in these bilayers, two qualitatively different type of Moiré patterns. The structure that's shown on the right-hand side here, in which you can see, if you look, if this is a chalcogen layer, the chalcogen layer below has been rotated by 180 degrees around the z-axis relative to the chalcogen layer above. And so this stacking between the layers actually has the lowest energy, and it's the thermodynamically equilibrium one. And, if you twist slightly away from this system, you get a Moiré pattern. But in this case, because I've rotated by 180 degrees, that means, what was momentum minus K, let's say in the bottom layer, becomes momentum K. So the momentum conserving tunneling is actually between states that have opposite spin. And for that reason, if you try to make a model of these Moirés when you have close to AB stacking, it's practically zero, okay? Yeah, go ahead. Yeah. So I'm getting there. Yeah, that's where we're going. So you can ask that question again in 2 minutes. I probably won't explain it. Okay. So I'm trying to explain why there's a skyrmion, a layer skyrmion, just in the single particle Hamiltonian in every unit cell. And, so that's a consequential property, and it's a nice little bit of serendipity. So that's where we're going. So just like I showed you on the blackboard, this interlayer tunneling, looking at the intra-sublattice terms, they vanish. Okay. I'm getting ahead of myself. Let me go back over here, okay? So what we're interested in here is this stacking between two layers that are not rotated by 180 degrees relative to each other. They're more or less lined up. And then this tunneling amplitude W here is turns out we got around 100 MeV for graphene. It's something smaller here. Details don't matter too much. But that's what's represented by these black arrows. And just like I showed you last time, this tunneling, to the same sublattice, which is relevant here, vanishes when you have local AB or BA stacking. So I'm going to say in a minute that, in these AA moires, you do have within the same unit cell, you have places within the unit cell which the two honeycomb sublattices are, stacked in the Bernal type arrangement. I'll come back to that in a moment, but stacked in the same way as graphene. When you have that kind of local stacking, the tunneling vanishes, okay? So that's, if you look at the arrows, the points here that I'll explain in a minute that are marked XM and MX, those are the points at which, in local approximation anyway, tunneling between the two layers at those positions within the Moiré pattern vanishes, okay? Now I can, now I'm interested in these two layers, rotated by 120 degrees, 180 degrees relative to each other. And we make a moiré, so we slowly change the stacking between the two layers, to locally displace one layer relative to the other. And let's say I displace the bottom layer. Here you can see when I take the bottom layer here, starting from this metal on metal configuration, and in the moiré, if I move it to the right a little bit, then I get a chalcogen in the top layer on top of the metal below, okay? At that position, as I just said, the tunneling will vanish for the exact same reasons we discussed in graphene. If I move bottom layer in the other direction, I'll get to a point where the metal in the top layer is right above the chalcogen below, okay? And at both those points, and they both exist in each unit cell of the Moiré pattern, as you can see from that illustration. And at both of those points, the local tunneling between the layers vanishes, okay? So now we have, I've talked about the off-diagonal terms in this Hamiltonian. The tunneling is, of course, a complex. This is a Hermitian matrix. But let me talk about diagonal term. And so what's the potential in the top layer? In the gauge that we've been using, the momentum transfers for tunneling between layers are these three Qs, which are basically reciprocal lattice vector plus the rotation of the K point. But within a layer, I just have some potential that's periodic. Really this is a tight binding model as a function of stacking. So this is an on-site energy for the metal as a function of stacking. That's what I really mean by delta of R. And, you can include lots of other orbitals in the tight binding model and include their effect perturbatively if it gives you a better description. But anyway, we just want this on-site metal atom energy as a function of stacking. And in this picture, I've actually chosen lattice vectors for the triangular lattice, which are, made the choice that they differ from each other from 60 degrees. So you can see that with the gauge, with the coordinate system I've chosen, one of the lattice vectors is in the y direction, so that means one of the reciprocal lattice vectors in the coordinate system that's chosen here is in the x direction, right? So I'm trying to look at this on-site energy as a function of stacking. It's a function that has to be, the on-site energy will return to the same value if I translate the bottom layer relative to the top by a lattice constant. So therefore, it has an expansion in reciprocal lattice vectors of this system. And let me call these reciprocal lattice vectors 1, 2, 3, 4, 5, 6, okay? Maybe I'll do 4. So to represent how this on-site metal energy depends on stacking, and if I want to, use the usual smoothness argument and truncate this Fourier expansion at the first shell, I still have seemingly, 6 complex coefficients that I have to represent, and this is an on-site metal energy. It's real. So when I do this Fourier expansion, just like normally for real functions, the coefficient for minus g has to be minus the coefficient of g. So 5 is not independent of 1, 3 is not independent of 4, and 6 is not 1, 2, 4 is not independent of 3, and 6 is not independent of 2. And also this system, it's basically a honeycomb lattice, and there's a C3 rotational symmetry. Even when you have the Moiré, there's still a C3 rotational symmetry. And so that means the Fourier coefficient for 1, 2, and 3, those coefficients have to be the same. So that means that this potential in each layer is determined by one complex number. And let me call that number, the magnitude of that complex number, V, thinking of it as something to do with a effective potential energy in the continuum model. And okay, so if I write delta G as V times e to the I psi and group together, G and minus G, I get an expression like this. So 2 parameters, basically. And in fact, this is a DFT calculation that this picture in the upper right comes from, and you can see that it's all very consistent with the smoothness assumption. So this is enough, really. So for TMD homo bilayer, valley systems, there are 2 of them, tungsten diselenide and molybdenum ditelluride. Then this is what the Hamiltonian looks like. And if I take D, I might get the sign wrong here. If I replace D by position, then this becomes a periodic effective potential that varies on the Moiré scale, okay, on a much longer length scale, basically expanded relative to the lattice constant, a microscopic lattice constant, and rotated by 90 degrees. Okay, so I just have one more thing to say about this model. Okay, one thing is, you might say that these let's say if I take this chalcogen on metal position, then this is, an electron sitting near a negatively charged ion in this system. And so that's going to make a potential that's repulsive for electrons and move the electrons up. Okay, so you might expect that this potential actually has its minimum at these chalcogen on metal positions. Okay. Okay. So only one more thing to say. So this was delta top of D, let's say, and delta bottom of D is delta top of minus D. So you can take the entire bilayer, just rotated around, for example, the y-axis by 180 degrees. So the two layers, change place, and yeah. So maybe I'm not saying this is exactly right, but you can convince yourself that the bottom layer is potential is just the top layer potential at the difference position. And, sorry, that should be D. Thank you. So as you can see in this illustration, and we were doing some of this stuff yesterday. In this real space picture, this is a primitive lattice constant, choosing this, parallelogram unit cell. So this is one primitive lattice vector. This is another primitive lattice vectors. Let's call it A1 and A2. And the distance you have to go to get from MM to XM is 1/3 of A1 plus A2. And mx is 2/3 A1 plus A2, or up to a lattice constant, it's minus 1/3, okay? So you move 1/3 of this A1 plus A2 distance in one direction, you get XM. In the other direction, you get mx. So that means that the potential in the top layer at the XM position is the potential in the bottom layer at the mx position. So so basically the structure of this Hamiltonian, and here I'm trying to come back to this question, why there's a skyrmion, so you can tell me if I've answered it. That if I think about this, this Hamiltonian, and now let me replace D by position. So this is a Hamiltonian in real position, and I use the usual Pauli spin operators for the layer degree of freedom. I can think of this system as having some potential, average of top and bottom, that can vary in space, but there's an effective magnetic field that acts on the layer pseudospin. At the XM and MX positions, this effective magnetic field, since there's no tunneling, is purely towards the North Pole, if I choose this layer representation, or purely towards the South Pole. So this is in the valence band, and we'll be interested in the first whole mini band. So we're interested in the highest states. And so the highest energy state locally will be have pseudospin Z at mx and pseudospin minus z at xm. And yeah, and if you think about how, it's only at those two positions that the difference between or that the tunneling between the layers vanishes. Tunneling between layers tends to be strongest at the positions. That makes sense because the metals are on top of each other. And so if you represent this local state, if you just ignore the kinetic energy for a moment and said, so the Hamiltonian is going to be, in this model, I'm just talking now about these local terms from the Moiré pattern, but in addition, there'll be a kinetic energy. If I totally ignored the kinetic energy, then, the lowest energy state would be for the spin to everywhere align with this direction of field. And the directions of this effective magnetic field cover the North Pole and the South Pole, and it turns out that they cover the entire sphere once when you integrate over each unit cell of the system, okay? So this texture in real space, the texture of delta of R in this model is, this is partly using terminology that's, common in the literature some of you may know on magnetic thin films, where people, which are borrowed from other places, of course, but this kind of texture in a magnetization direction that covers, the entire block of pseudospin directions is called a skyrmion. And the property of the real space texture is that the integral over a unit cell, any unit cell in real space, is the sometimes called Pontryagin index density. You can see that it's just a little element of area covered on a unit sphere per little region in space. And if you integrate over entire unit cell, for this texture, you'll cover the sphere once. Okay? I'll come back in just a second for questions. This is a good time. But let me just make a couple more remarks. So this is so we can call this a skyrmion lattice Hamiltonian with one skyrmion per unit cell. In magnetic thin films, people make skyrmion lattices all the time, and they hope the future magnetic technology. But it's one skyrmion for every 10,000 unit cells, okay? So this is quantum, in some senses, already quantum skyrmion. And okay, so let me stop there and we'll go to questions. Go ahead. Yeah, a torus to a sphere, yeah. Well, in no way I know of. I can to tell you, make a statement that I'm 100% sure is correct. Yeah, I don't think so. But it's a topological index, which is a map from of a map from a torus, a unit cell, to the block sphere of directions. Yeah.
My question was just when you're heat plotting this cosine, and you just use DFT to fit psi and v, or if you build, like, do I know? And is it just that simple, or we know that that's what actually happens in real systems?
Yeah. So let me be historically accurate. So when this is actually a plot from the first paper on these AA homo bilayers. And what we did at the time is we just argued phenomenologically, building on what we did with graphene, And we did band structure calculations for all the high symmetry stackings, and then we fit it, okay? But, the way we do it now, and we certainly have done this over again, you can do a DFT calculation for every stacking. And this is a partial representation of at least the layer dependent. This is a representation of the layer parts of the tight binding Hamiltonian as a function of stacking. Yeah. And, the phenomenological approach, just using the high symmetry points, since the number of parameters is so small, works perfectly fine. Just like in the graphene case, there's lots of questions of detail about the DFT. One of the most important being, strain relaxation on the Moiré scale, which I'm not discussing here. And so that's turns out important when the Moiré period is very long. And so there are other little things. So, the actual parameter model are not completely universal because of strain effects. They depend on twist angle. I might get to that eventually. And the actual numbers have been refined from the initial estimates. So let's go. I'm not sure. I think your hand was up first. So let's go with you.
On sigma?
Yeah.
Are you including the Pauli matrix in this?
Yeah. So that's just a representation of this 2x2 matrix. And I think, the two Pauli matrices that are off diagonal are sigma x and sigma y. So delta x is basically the real part of this tunneling amplitude. And delta y is, as I've written it, minus the imaginary part. Yeah. Delta. Okay. So there's an average value of the deltas. Turns out there's no symmetry that requires this to be 0. I've written it as delta top of R plus delta bottom of R, but it could be delta top of R plus delta top of minus R. So this has some dependence on position. And actually, if, for example, it's all carried, whoops, I think I've covered stuff up. The thing that depends on the microscopics is the magnitude and phase of this expansion coefficient, which is capturing the shape of this potential. And so if psi were 90 degrees, then it turns out, the bottom layer, this condition means you get plus or minus psi. And so if the fitting parameter psi were 90 degrees, then that would mean that delta top plus delta bottom was always 0, or always constant anyway.
Yeah, I was also interested in what's the modulus of delta vector.
Yeah, so
I would have thought for skyrmion, you need it to be like pressed if it's always so that n.
Yeah. So we need what you're saying is the magnitude of this non-zero everywhere, and the answer is generically within this model. Generically, yes. Okay, it's non-zero everywhere because there are these positions xm and mx at which the tunneling vanishes. But then there's a big difference between the potential in the two positions. And if you go to the sort of green region of this picture, which is close to metal on metal, then you have strong tunneling from layer to layer. Yeah. Now, there are competing effects that occur as a function when you include, and it can be that there's the sign of delta Z can change. And so whenever it's changing, what that means is that, that at the XM and MX positions, the difference in the energies of the two layers, in some regions of the phase space, at least some people have argued, it can get small and can change sign. And in that region, the skyrmion picture wouldn't work. But generically, it does. Go ahead.
This topological invariant, the 4 pi that you wrote.
Yeah.
Is that related to something in the electronic sense?
Yeah. So this is, if you go back to the magnetic thin film skyrmion literature, they always argue, and I'm going to come to this, looks like next time, if I restore the kinetic energy, and think about moving through space, and I have this, let's say, in the limit of large magnitude of delta, or large Moiré period, the local layer pseudospin will just follow the direction of delta. And so as a function of 2D space, I'll get a Berry phase if I go around a closed path. And if I go around the unit cell, because I have this, I'll have 2 pi Berry phase in each unit cell. And remind me your question again was, okay, so connected to anything. Yeah, so, in the magnetic thin film literature, they interpret the skyrmion texture just like I'm going to do next time as an effective magnetic field. And they say that effective magnetic field will give a Hall effect. And they refer to this as the topological Hall effect, okay? So here, we can know everything about the fluid interactions. And, quite generically, the real space Hamiltonian has this texture. You might expect that this would lead, in momentum space also to a texture as a function of momentum and to which from, David Thales gives the, the Berry phase in momentum space gives a quantum Hall effect, the Chern number of the band, if you like, okay? So when you look through the parameter space of, these 3 parameters that I mentioned, W, and B and psi, 3 parameters in the simplest version of this model, there's not a one-to-one, you always have a texture in real space, and mostly you have a texture in momentum space, but they don't match one-to-one. Sometimes bands can overlap and it's not an insulator. Yeah. And okay, I'll maybe make that remark later. Go ahead. No. So they're basically the interlayer tunneling in the case of AB stacking should be extremely weak because you're coupling between opposite spins. And if you apply the local stacking approximation approach that I've been describing, there is no tunneling between the layers. There is, people have made some interesting observations also in AB homolayer Moirés that I'm not talking about. Perhaps not quite as spectacular as the ones I'll be telling you about. And they've argued that there is some small interlayer tunneling. I'm thinking of Burke and Liang Fu's group. Who's the first author, Aidan?
Sorry, of which paper?
About trying to understand the quantum anomalous Hall effect in the AB stacking case.
Oh, Yang Zhang?
Yeah, that's right. He's at University of Tennessee, right? Yeah. So people say there is some tunneling, but it's very small. So, and, sort of, as I've been saying before, when things get small, then there are all kinds of little uncertainties, and it's more difficult to be confident you know what's going on. So in the AA stacking case, there's strong interlayer tunneling. So we know more or less what's going on. Follow? Yeah. Yes, probably. Yeah, I will certainly argue that that's the case. Okay, good time to stop?
Yes.
Yep. Okay.